used in mandolin. The mandolin, a stringed instrument known for its bright and crisp sound, relies on mathematical precision in string tension, fret spacing, and tuning. Let's explore how math shapes the mandolin's structure and sound. Mandolins use math in string length and frequency. The frequency of a vibrating string follows the equation F equals 1/2 L under root T mm, where L is string length, T is tension, and mu m is mass per unit length. Shorter, tighter strings produce higher frequencies, while longer, looser strings generate lower tones. Fret placement and scale length. Frets divide the string into precise lengths to produce musical notes. The placement follows a logarithmic pattern based on the 12th root of 2, 1.059, ensuring equal temperament tuning across the fretboard. Soundboard and resonance. The mandolin's body shape and materials affect how vibrations amplify sound. Mathematical models help luthiers, instrument makers, optimize the resonance chamber for rich, clear tones. String tension and bridge positioning. The bridge transfers string vibrations to the body. Its position is mathematically calculated to balance string tension and ensure accurate intonation. Mathematical principles applied. Harmonic series defines frequency relationships between notes. Logarithmic functions determine fret placement for equal tuning. Wave physics helps optimize resonance for a richer sound. Through mathematical precision, the mandolin achieves its signature bright tones, blending art and science in perfect harmony.